Right, let's see how this goes. I'm going to go slow, and I'm really interested in this amazing story about the two girls in America, two high school girls in America, who've come up with a proof of Pythagoras that uses trigonometry but doesn't rely on the identity sine squared plus cos squared equals 1. So first of all, I want to make sure that I credit them. And I'm going to have to edit this video. You know I am. So it's high school Pythagoras proof. 1, 2, 3, 4. Sounds okay. The Guardian are the ones that have been covering this. Right. Okay, I'm not sure how to pronounce the names. Kelsey? That makes more sense than Calcia, but Kelsey Johnson and Nakia Jackson. Johnson and Jackson, or Jackson and Johnson. So we'll try and remember that. Johnson and Jackson, or Jackson and Johnson. Okay, here we go. So the first thing I wanted to look at is, why are people saying that this identity sine squared of an angle plus cos squared of an angle equals 1? So why would you not be allowed to use this? So let's have a quick look. We should... Let's do this first. Make a triangle. A right-angled triangle. It's not going to be perfect. I'll change colour. So let's put an angle here. Theta. And this would be the opposite side, this would be the adjacent side, and this would be the hypotenuse. So at school, you learn that the sine of the angle would be opposite over hypotenuse, and the cos of the angle would be the adjacent over the hypotenuse. I should have used x for the angle, shouldn't I, to tie in with this? But anyway, so let's have a look. Sine squared of the angle plus cos squared of that angle would be the same as opposite over hypotenuse squared plus adjacent over hypotenuse squared. How's my sound? 1, 2, 3, 4, 1, 2, 3, 4. It's not too bad, is it? Okay, a bit quiet probably. I'll bring the mic over towards me a bit. Okay. Sine squared plus cos squared is equal to that. Okay, we can rewrite this as O squared over H squared plus A squared over H squared. And then we've got two fractions with a common denominator. Common denominator. So that means we can write them as O squared plus A squared over H squared. So at this point, we'll look back here and say the claim is that this and this are equal to 1. And that relies on Pythagoras, because it relies on the fact that O squared plus A squared equals H squared. So if you think about that for a moment, Pythagoras, right angle, forgot that. Pythagoras says that if you square this and you square this and you add them together, then you get this squared. And if these are the same as each other, then the top of this is equal to the bottom. And any fraction that has, let's say 5 on the top and 5 on the bottom, well, that's equal to 1. So that's why you can't use this identity. If you rely on this identity, then you're relying on Pythagoras, to prove Pythagoras. And so then it's a circular theorem or a circular reference, or it's a circular argument. Okay, right. So I wanted to cover that. There's a really neat proof of Pythagoras that I normally go through with my students, but let's just jump in and have a go at this new one. I'll try and make a nice right-angled triangle here. Oh boy, already failed. Maybe I should do the base for... failed again. Right. I really do want this to be on the lines. Oh boy. You know I'm going to have to edit this, don't you? Okay, that'll do. Don't want it to be too big. There, that's pretty good. Pretty good base, I think. Okay, and then let's go to this corner here. Right, so this is the triangle. This is our right-angled triangle. So we're going to have an A, a B, and a C. We're going to call this angle alpha, and this one beta. 1, 2, 3, 4, 5, 6, 7, 8. It goes 8 across. Three, 4, 5, 6, 7, 8. There we go. Oh no, that's no good. It needs to go right across this line. See, we're taking our time here. That's it. There's 8. We've just extended it to an identical right-angled triangle. So we've added an identical right-angled triangle, turned it into an isosceles triangle. Because we have, let's get this right, we've got a right angle here. It's mirrored, so there's a angle beta is here, and alpha is here, and C is here, and A is here. Okay, so this is how it starts. Right. The next thing, I don't know if this is going to work visually, because the next thing is that we continue this line down. So what I want to do actually is start from the top. Keeps switching off, doesn't it? So we're just continuing this side, the right hand C side, all the way down. And now we need this to be, we need this to be at right angles to C. Okay, that looks good. That looks okay, doesn't it? I'm going to cross them over like that, and then I really want to make a point that this, undo, need to switch to the pen. Okay, this is a right angle here. Okay, so we've made a bigger right-angled triangle. It's not quite the same as the old triangle because it has, in this corner here, for example, it has the angle 2 alpha. And in this corner, well, this is the next challenge. So let's keep with the red for now. And we're going to go like this. Now at this point, we can say that this triangle here is similar to this one. Why can we say that? Well, this line carries on down like this. This one. So we definitely have... Yeah. Of course it's similar, right. So let me just... So we can say for sure straight away, because this goes straight down, this goes straight across. We've got the right angle here. Because this is a continuation of this line, we have beta here, and we have alpha here. Yes. Similar triangle. Then the next one, it's flipped, but I think it's similar again. I'm not going to try and pretend any of this is obvious or easy. I don't think that helps anyone, but I don't know, sometimes you get, if the video does get any views, you get all sorts of comments. But let's take our time. So we're creating an infinite sequence of triangles. Like this. In the presentation images, you can see that, was it Johnson and Jackson or Jackson and Johnson, have described this as a waffle cone, which I loved. Okay, that's the best I can do. That's not too bad, is it? Are we still recording? Yep. All right. Now let's see what we can find out about this triangle here. What do we know about this triangle? Well, it's got 2A across the top. It's got a right angle here. We don't know the height of it. Well, I don't think this is the way to do it, but 90 minus beta, we know that to be true. Ooh. In a right angled triangle, these two always add up to 90. So that means that's beta. But how? Oh, no. But it is. Seems a bit strange. But if this angle round this corner here is 90, and this angle's beta, then all the way around here is 90. Take away beta, you get this one. This is 90 degrees. So this angle here is definitely beta. Progress. Okay, and then we can say, right, there's some things to do here. So let's say we want to know this length here, which is the hypotenuse from here to here. So we'd write something like sine of beta equals opposite over hypotenuse equals 2a over, should we call it x? Right. So then x would be 2a over sine beta. But then we already have, oh yeah, from this triangle here, we've got sine beta equals opposite over hypotenuse is equal to b over c. 2a over b over c. Then we're going to keep flip change, KFC. So let's do that. So then we get x equals 2a times c over b equals 2ac over b. Boom. Okay. So I want to clear all that because I'm going to have to keep this drawing. Okay, we're pretty confident on our calculations there, aren't we? So if I hit Z, 2AC over B. 2AC over B. Oops. Okay. I'll erase instead. Two AC over B. Nice. Now, can we do something similar? Can't use Pythagoras. So what are we trying to do now? I know. Oh boy. If this is alpha here, and this is beta, is it really that? Are we going to have to find this side here first? I don't remember seeing anyone do that, but everyone's kind of really sped through this that I've seen. So let's try it. So this is our new x. So we've got cos beta equals adjacent over hypotenuse cos of beta equals x over 2ac over b. But cos beta also is equal to b over a. No, a over b. Adjacent over, oh my god, a over c. Mistakes have been made. So I'll write that here. A over c. Okay, so we've got a over c equals x over 2ac over b. Oh boy. X equals a. Oh, I gotta be really careful here actually. A 2ac over cb. Ooh, this is getting good. Equals 2a squared over b. That's right, isn't it? I'm going to change colours. Two a squared over b. Okay. 2a squared over b. All right. Let's clear that. And we now have sine beta, which we already know is b over c, is equal to opposite over hypotenuse, which is now 2a squared over b over this hypotenuse. Over, we'll call it x again. All right. All right, so bring the x up to here. So x equals c over b times 2a squared over b equals 2a squared over b squared times c. Okay. is looking good. 2a squared c over b squared. Okay. It's so tempting to use Pythagoras, isn't it? It really is. But you have to just keep using trig all the way down. So the next thing would be that you would need to know the length of this. And then you'd use that to find... Oh, wait. So I can put that this is angle beta again, can't I? Actually, can I? Yes, because this one we've already shown that this triangle has a beta here. How is it even possible? Which means it must have an alpha here. Ooh. Because they're similar triangles. Yes. Okay. Breakthrough. Alpha. Beta. Alpha. Beta. Alpha. Beta, and so on. Alpha. Beta. All the way down. 90 minus beta is alpha. Definitely. Yeah. Right. What now? Clear some space. Cos beta equals adjacent over hypotenuse. This is our new x here. Equals x over, oh god, 2a squared c over b squared. But we also know that cos beta equals a over c. So, all right, x equals a over c times 2a squared c over b squared. I'm starting to see how this a over c is going to be the common ratio of a geometric series. So if this 2a... No. So... adjacent x over hypotenuse x will be equal to cos beta equals x over that equals a over c. X equals, right, 2a cubed over, oh, so the c's cancel again. Oh, b squared. Change colour again. This is going to get really difficult to write. What I'm going to do, I'm going to bring this triangle out. and we'll work on it out here. So what do we know? We've got beta here, alpha here, and we've got our top side now. Something doesn't feel right. Cos of this angle is equal to the unknown side divided by the hypotenuse, adjacent over hypotenuse. And okay, all right, AC 2a cubed, 2a cubed. Okay. 2a cubed over b squared. Okay, so now what we would like to know right. So now we've got sine beta equals opposite over hypotenuse equals, and we'll call this x, 2a cubed over b squared. That's opposite over hypotenuse. But also we know that the sine of beta equals b over c. Oh, that's messy. Okay, so the x goes up over there, and then these, so we get x equals c over b, 2a cubed over b squared equals 2a cubed c over b cubed. Oh yes, 2a cubed c over b cubed. Two AC over B is this one from here to here, and then 2a cubed B over C cubed is this one here. So when you go from here to here, it's times a squared over b squared. And when you go from here to here, it's times a squared over b squared. So how many of these are we actually going to work out? One more. But if that's the scale factor when you go from one to the next, then it's going to be the scale factor when you go to the next, to the next, to the next, isn't it? All right, would like to spend more time on this, but let's get on to the next bit. There's still two major kind of unknowns. Yeah, let's figure out the next steps. Okay, I see it. Do we want this? So let's just write in. Okay. The length of this side here is the sum of a geometric series. So you've got I don't know what to call it. I think it should be called Big B is this side, and Big C is this side. So we've got the length big B is equal to the sum of some, what is it, a r to the n minus 1. The sum of a geometric series. Sum of a geometric series. Okay, equals. Right, the first term is 2ac over b. And then actually let's put the second term is 2a cubed b over c cubed. And the third term must be 2a to the 5 b over c to the 5 and so on. We're still recording. Long ass video. No one's going to watch this. Okay. 2ac. Ooh. Ooh, no. Something's gone wrong. Oh, something's gone wrong. Or has it? I gave up too early on looking at the sequence. Yeah, something's not right. If it was 2a cubed c over b cubed, I think I've made a mistake. Let's go back. This really needs to be 2a cubed c over b cubed. I'm going to go back a couple of steps. Right. I feel like checking everything now. Okay, let's just go back and just remind ourselves of what's going on. So we now know we've got alpha and beta here. We've got a right angle there. I'm doing everything with beta. Yeah. Triangles look good. A little bit surprised. Yeah, no. Okay. So we said sine beta, which is b over c, is also equal to sine opposite over hypotenuse 2a over x. So that gave us x equals 2ac over b. Okay, so that one's fine. Okay. Then we do cos beta, which is a over c, is equal to adjacent over hypotenuse x over 2ac over b. So we then get x equals 2a squared c over bc. The c's cancel, and we get 2a squared over b. Lovely. So that's that one. It's getting a little bit quicker now. Then we do this thing. So we say sine of beta, which is b over c, equals opposite over hypotenuse, which is 2a squared over b over the thing we want to know. So then we do a swap. Okay, we bring the x up to here and we do c over b times 2a squared over b. We get 2a squared c over b squared. And we're happy with that. Okay. Keep going. Right. Now, we have a triangle that we know two sides in it. We have a right-angled triangle that we know two sides in it. So we could, not using tan, we can use, again, adjacent over hypotenuse. So we've got cos of b, which is also a over c, is equal to the adjacent x over the hypotenuse 2a squared c over b squared. ab squared over 2a squared c squared. No, wrong. Wrong. X equals a over c times 2a squared c over b squared. 2a cubed, c's cancel, over b squared. It's just writing it in, isn't it? I know, arrows. A cubed over b squared. Okay. Now, sine of beta is opposite over hypotenuse. B over c equals the opposite 2a cubed over b squared over the hypotenuse, which is the thing we want to know. So we get x equals c over b 2a cubed over b squared. And again, we get that times by c over b. Oh, yes. Equals 2a cubed c over b cubed. Now that's better. 2a cubed c over b cubed. I'm feeling lucky. So now, to get from here to here, we've multiplied by a over b. So I messed up somewhere last time. So I think the idea is, and we could repeat it one more time, but no, there's still a problem. Okay, so I'm now happy with this sequence. This sequence is very likely to be 2a to the 5 c over b to the 5, and then 2a to the 7 c over b to the 7, and so on. We've got a scale factor of a squared over b squared each time we go down. So then the question is this side here 2a to the 4c over b to the 4? I think we need to check that. What do we have? Yeah. I've got to draw the triangle like this. That's bad. Change color. See how we get on with orange. Okay. So now we've got cos of beta, that's a over c. A over c equals adjacent 2a cubed c over b cubed over the hypotenuse. No. The adjacent is the thing we want to know. And the hypotenuse is 2a cubed c over b cubed. So then we get x equals ab cubed over 2a cubed c squared. Cross out the a's. Don't like it. Don't like this one bit. Let me just check this. Cos is adjacent over hypotenuse, which is b a over c. A over c equals the adjacent over the hypotenuse. Okay, so we've got, cross out the a's. So this side here is 2. Really? I've messed up again. This is getting silly. Yeah, I didn't like that answer because it was wrong. Okay. X equals 2a to the 4 c over cb cubed. Thank you. Yes! So we have a scale factor now of, cross out the c's, 2a to the 4 over b cubed. Yes. So this side has been multiplied by a squared over b squared. So the same thing's going to happen to this side, but let's just check. So we got beta here. Okay. Change color. I'm just going to go black. Right. Right. Sine of beta, which is b over c, equals opposite over hypotenuse over the thing we want to know. Here. So x equals, so the x goes up to here, 2a to the 4c over b to the 4. Yes! All right. 2a to the 4c over b to the 4. So I think once we've established the scaling happening once, I think it's enough. I think it's enough. You could keep going and you'd see the pattern. Wow. Right. Let's clear some space. Get rid of that. So we have a triangle now that's these two sequences. So I had the idea of calling this big B, this full length here, big B, and this full length here is big C. So big B is 2AC over B. I need more room, I need more room. Two AC over B plus 2A cubed C over B cubed plus ... We have first term is 2AC over B. That's first term over 1 minus the common ratio. So if I put it up here, if you have a sequence that goes A plus AR plus AR squared plus AR cubed plus ... all the way to infinity, the sum of that is just A over 1 minus R. So you have your first term and then 1 minus the common ratio. Okay, so we'll simplify that. So you've got 2AC over B, and then that's over B squared minus A squared over B squared. Flip them over. Oh, I haven't got room for this. Go up here. Two AC. Nope. 2ABC. Two ABC. Don't like the look of that. This big triangle is similar to the smaller triangle. Okay. So I might have to clear some stuff out again. So we think that the side B is equal to so it was 2AC over B over the common ratio, which was so 1 minus the common ratio. I'm going to run through that again. I know it sounds crazy, but I'm going to run through it again. Right. So it's A over 1 minus the common ratio. Yeah, okay. Then you get 2ac over b all over b squared minus a squared over b squared. Then that becomes 2ac over b times b squared over b squared minus a squared. So you end up with, I'll write it over here, 2abc over b squared minus a squared. B, that's B. 1, 2, 3, 4. Okay, still recording? Right. Next thing, C. So the sequence C has a first term A, C, sorry. Then it gets into the sequence. Okay. So you've got C plus, and then I think you factorize out to C. And then you've got a squared over b squared plus a to the 4 over b to the 4 plus. Is that right? C plus 2c times all of that stuff. Once again, we can use a, which is a squared over b squared, over 1 minus the common ratio, which is a squared over b squared. Is that right? I need to tidy that up. Let me clean this up. How are we doing? 54 minutes. Wow. C plus 2c times a geometric series that starts a squared over b squared. What about, is it better? It's the same. So that's going to give us big C. So that looks like beta, doesn't it? Big B is equal to this, and the big C is equal to 2 a squared C over b squared times 1 over 1 minus a squared over b squared. Oh, the b squareds cancel. At least that happens. So we have 2 a squared C over b squared minus a squared. That doesn't look good. I keep saying that, but I'm less confident of this sequence than I was with the other one. Okay. Okay, now the difficult last few steps. We have the sine rule. So there's something about big B over big C is opposite over hypotenuse for 2 alpha. So sine 2 alpha is equal to this thing, 2abc over b squared minus a squared over 2a squared c over b squared minus a squared. This doesn't look right because these cancel and you get the 2's cancel, the c's cancel. Oh god. Does that just become ab over a squared? Oh. A over a squared. It says that's just b over a. Which we know. No, we don't. We don't know that. Oh no, that's just gone wrong. So for 2 alpha, opposite is this sequence B, and the hypotenuse is the sequence C. We take the quotient B over C, opposite over hypotenuse, and that's sine 2 alpha. I'm sure that's the right thing, but it shouldn't come out. B is 2abc over b squared minus a squared, and c is 2a squared c over b squared minus a squared. It's supposed to have a squared plus b squared on the bottom, I thought. Okay, well, let's just keep going. In this big triangle, we have 2a over sine 2 alpha equals c over sine beta. But sine beta is b over c. Okay. 2a over sine 2 alpha equals c over... I need to clear some of this. I need to clear up a bit. Right, using the sine rule, we have 2a over sine 2 alpha equals c over sine beta. 2a over b over a, because that's sine 2 alpha, equals c over sine beta, b over c. This hasn't worked. 2a squared over b equals c squared over b. Oh, what a shame. It's so close. But it's not really. 2a over sine 2a equals c over sine beta. Sine beta equals b over c. And sine 2 alpha equals b over a. I think I missed something. I think I know where it is. I think I know what I missed. So I'm going to go back. And I'm going to work through the two sequences again. So I don't think this is right. And I don't think these are right either. Still recording? Right. I think I've got the right sequences. I just don't think I've summed them correctly. So 2ac over b times 1 over 1 minus a squared over b squared. Yeah, that one seems relatively easy. So you've got 2ac over b squared minus a squared over b squared. So you've got 2ac b squared over b squared minus a squared b. So you've got 2abc over b squared minus a squared. Right, so that's big B equals 2abc over b squared minus a squared. Now for the difficult one. Right. So we've got C plus a sequence. I think I just calculated the sequence. So plus 2a squared c over b squared times 1 plus a squared over b squared plus, okay, c plus 2a squared c over b squared, that's a times 1 over 1 minus, I did it again, 1 minus a squared over b squared. Okay. Times 1 over b squared minus a squared over b squared. So the big C equals C plus 2a squared c over b squared times b squared over b squared minus a squared. Okay. Equals c b squared minus a squared plus 2a squared c. Over b squared minus a squared. So again, we're now into doing the sine of this angle, which is the big B over the big C. Sine. Wait, I need to tidy this up. Equals C B squared minus A squared. Oh, why didn't I? CB squared minus CA squared. CB squared minus CA squared plus 2A squared C over B squared minus A squared. Check my phone. Okay. Do some erasing. Equals. CB squared plus CA squared over B squared minus A squared equals C brackets, let's call it what it is, A squared plus B squared over B squared minus A squared. That looks good. That looks good. C times A squared plus B squared over B squared minus A squared. There we go. Change color. Let's try this green. Okay. Sine 2 alpha equals opposite over hypotenuse. B over C. Sine of 2 alpha is equal to, cross them out, 2abc over ca squared plus b squared. Cross out the c's, equals 2ab over a squared plus b squared. Is this going to work? But also, from the sine rule, we've got sine 2 alpha over 2a equals sine beta over c. Okay, sine 2 alpha over 2a equals b over c over c. Okay, I need to clear some space here. I need to clear some space. Sine 2 alpha is 2ab over a squared plus b squared. But also from this, sine 2 alpha is also equal to 2a times b over c squared. Now, sine 2 alpha is equal to sine 2 alpha. So that means we get to write 2ab over a squared plus b squared equals 2ab over c squared. And these two things are the same. So these two things must be the same. And that's the answer. A squared plus b squared equals c squared. That seems like a good place to stop.